Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I mean, pretty much every textbook on Earth says that when a massive star dies, that it becomes a black hole.
Right. It's essentially presented as an absolute fact.
Yeah, exactly. We are taught that it becomes this cosmic graveyard, like a bottomless pit of gravity where light, matter, information, all of it just gets crushed completely out of existence forever.
A total dead end in space-time.
Right. But what if those textbooks are, fundamentally wrong?
Well, that's the trillion-dollar question right now.
It really is. Like, what if you took that image of ultimate destruction, that terrifying void, where the laws of physics just snap in half and flipped it entirely on its head?
It's a radical shift in perspective.
Totally. I want you to imagine that this exact same spot of absolute collapse isn't a graveyard at all. What if, instead, it's a delivery room?
A delivery room for a new universe.
Yes. The birthplace is something entirely new, something so radically bizarre that it completely rewrites the story of the night sky.
The implications of that shift, they really cannot be overstated. We are looking at a scenario that challenges the most entrenched dogmas of astrophysics.
Which is saying something, because physicists love their dogmas.
They do. They really do. But this isn't just about tweaking a minor variable in some, distant, esoteric model of the cosmos.
Right.
We are talking about fundamentally solving a 25-year-old mystery in theoretical physics.
A quarter of a century.
Exactly. By rethinking the ultimate fate of massive stars, we are forced to rethink the fundamental nature of space-time itself. The stakes here, both mathematically and philosophically, are absolute.
Okay, let's unpack this.
Okay.
Because this topic completely reframes everything we thought we knew about what happens out there in the dark.
It really throws a wrench in the standard narrative.
It totally does. We are talking about the end-of-life cycle of massive stars, and specifically a newly formulated mechanism where dying stars don't just quietly collapse into the black holes we've always taken for granted.
Right.
But instead, they might spawn entirely new, dark energy-filled mini-universes. I mean, the idea of a universe existing inside the corpse of a star is, it's something that requires some serious mental gymnastics.
Oh, it demands a complete departure from our everyday intuition, without a doubt.
Yeah, to put it mildly.
But to truly appreciate the elegance of this new theory and, to understand why theoretical physicists are so captivated by this idea of internal mini-universes, we really first have to thoroughly dismantle the standard story.
We have to tear down the textbook.
Exactly. We have to look at the accepted wisdom of how stars die, and crucially, we need to understand the catastrophic mathematical and physical headaches that this accepted wisdom has been causing for decades.
Right, because the textbook version has some, glaring plot holes when you actually look at the equations.
Yeah.
The math starts screaming at a certain point.
Screaming is a very good word for it, yes.
But before we get to the death of a star, we have to talk about its life. From my understanding, a star's entire existence, a life spanning billions of years, is essentially just one long, incredibly violent cosmic tug-of-war.
That tension is the defining characteristic of any star. A star, whether it is our sun or, say, a blue supergiant 50 times more massive, it is not a solid, static object.
It looks solid from here.
Right. But it's really a churning, chaotic sphere of fiercely hot gas and plasma, and its entire existence is defined by a delicate state of hydrostatic equilibrium.
Hydrostatic equilibrium. So the tug-of-war.
Precisely. On one side of this relentless tug-of-war, you have gravity. A star contains a staggering amount of mass.
Just astronomical amounts.
Literally. In extreme cases, we are talking about structures millions of times the mass of the Earth. All of that mass generates a colossal gravitational field.
And gravity only wants to do one thing.
Exactly. It has only one singular goal, which is to pull all of that matter inward, trying to crush the entire star down into an infinitely dense center.
Gravity is just constantly trying to close its fist.
Yeah.
It never takes a break. It is always pulling inward.
Always, every single second for billions of years. But gravity doesn't immediately win because it faces an equally terrifying opponent, the star's internal engine.
The fusion reactor.
Right. Deep within the core of the star, the immense weight of the outer layers creates pressures and temperatures that are so extreme, we're talking tens of millions of degrees, that the fundamental repulsion between atomic nuclei is actually overcome.
Because usually atoms want to bounce off each other, right?
Exactly, they repel. But under this crushing weight, hydrogen atoms are violently smashed together to form helium.
And that's nuclear fusion.
That's fusion. And this process releases an almost incomprehensible amount of energy. According to Einstein's famous equation, E = mc squared, a tiny amount of mass is converted into a vast amount of pure energy.
And that energy has to go somewhere.
It does. It radiates outward from the core in the form of high-energy photons. We call this outward push radiation pressure.
So you have the fist of gravity trying to crush inward, and like the blast of a billion continuous nuclear bombs pushing outward.
That is a very accurate way to visualize it, yeah.
And as long as the star has fuel to burn, that outward push balances the inward pull. The star shines, it stays a sphere, and it is stable.
It's in equilibrium.
But the fuel isn't infinite, right?
But it's fiercely finite. Over millions or billions of years, the star burns through its hydrogen, then its helium.
It just works its way up the chain.
Right, moving up the periodic table, fusing heavier and heavier elements, carbon, neon, oxygen, silicon, all just to maintain that outward radiation pressure.
It's getting desperate at that point.
Very. But eventually, a massive star reaches iron, and iron is the ultimate cosmic ash.
Because iron doesn't burn, does it?
No, fusing iron doesn't release energy. It actually consumes energy.
So the nuclear engine just stalls out. The gas tank is entirely dry.
Utterly dry.
And the moment that happens, the outward radiation pressure just vanishes.
Yeah.
Right? The tug of war is over. Gravity's the only player left on the field.
At that exact moment, the core of the star collapses under its own immense weight. The outer layers lose all their support and come crashing inward at a significant fraction of the speed of light.
Whoa. A fraction of the speed of light.
Yes. This isn't a slow deflation, you know. It is a catastrophic, instantaneous free fall of billions of trillions of tons of matter.
I sometimes picture it like a hot air balloon. Like if you were up in the sky, the burner is blasting that hot air, which is our nuclear fusion, our radiation pressure.
Right.
And it is keeping the balloon inflated against the immense weight and pressure of the atmosphere, pushing against it from the outside.
Sure.
But if that flame goes out suddenly, the heat dissipates, the pressure drops, and the atmosphere just crushes the balloon.
That makes sense.
Except in the case of a star, it isn't an external atmosphere crushing it, is it? It is the star's own internal gravity pulling its fabric violently toward the center.
The balloon analogy gives us a really good visual of equilibrium failing, but we have to scale up the violence of the collapse exponentially.
Right, way more violent than a balloon.
Unfathomably more violent. When a massive star's core collapses, it crushes the atoms so tightly together that electrons are literally forced into protons, creating a solid ball of neutrons.
Which is insane density.
Exactly. Sometimes a shockwave from this initial collapse blasts the outer layers away in a supernova.
One of the brightest things in the universe.
Right. But if the remaining core is massive enough, typically more than 2 or 3 times the mass of our sun, even the repulsive force between neutrons, known as neutron degeneracy pressure, is overwhelmed by gravity.
Gravity just overpowers everything.
It does. The collapse doesn't stop at a dense core. According to the standard textbook model, general relativity dictates that the matter crushes down smaller and smaller.
Shrinking infinitely.
Past the size of a planet, past the size of a city, past the size of a pinhead, until it collapses into what we call a singularity.
A singularity.
A single point of zero volume and infinite density. The absolute heart of a black hole.
And right there, that word singularity, that is where the plot holes in the textbook start to show up, isn't it?
That's the core of the issue, yes.
Because just saying the words billions of tons of mass crushed into zero volume feels inherently wrong. It feels like, dividing by zero on a calculator.
Exactly.
You get an error message. It feels like a glitch in reality.
What's fascinating here is that theoretical physicists completely share your skepticism. They have been deeply uncomfortable with the concept of a singularity for exactly that reason.
Oh, really? I always thought physicists just accepted it.
Not at all. That glitch is precisely what has tormented theoretical physicists since the concept was first mathematically formalized. To understand why a singularity is so problematic, we have to look at what it actually implies for the fabric of the universe.
Okay, let's get into it.
Einstein's theory of general relativity tells us that mass curves spacetime.
Right, the classic trampoline analogy.
Exactly. Think of a heavy bowling ball sitting on a trampoline. It creates a dip. The more concentrated the mass, the steeper and sharper the curve in spacetime.
Makes sense.
Now, if you take the mass of an entire star and concentrate it into a mathematical point with literally zero volume, the equation for the curvature of spacetime at that exact point outputs a terrifying value.
Infinity.
Infinity.
Infinite curvature. A literally bottomless pit in the trampoline.
Yes. And in the realm of physics, whenever your equations start outputting infinity, it is universally recognized as a massive red flag.
Like the math is broken.
Precisely. Nature abhors an infinity. An infinite value usually means that the mathematical tool you are using has been stretched completely beyond its applicable limits.
It's just out of its depth.
At the singularity, the known laws of physics completely and utterly break down. General relativity essentially predicts its own demise. We lose the ability to predict what happens mathematically, mechanically, or physically.
But wait, if the laws of physics literally break down at the singularity, isn't that just a fancy academic way of saying we have absolutely no idea what happens next?
Yes, essentially.
It is like those ancient maps that just said, here be dragons at the edge of the ocean.
Yeah, that's a very apt comparison.
So the singularity isn't necessarily a real physical object, right? It is just a monster we've drawn on the edge of our mathematical map because our equations just can't see past that point.
The overwhelming consensus is that a singularity is a mathematical artifact, a failure of our current models, rather than a tangible physical reality.
Okay, that's huge.
It really is a neon sign screaming that general relativity is incomplete, likely because it entirely ignores quantum mechanics, the physics of the incredibly small tile, which must surely dominate when matter is crushed to such an extreme degree.
And it isn't just the singularity that is frustrating, right? There's a curtain that drops around it, hiding the evidence. Because we can't even look at a singularity to see what it is actually doing.
You are referring to the event horizon.
Exactly.
When a mass becomes dense enough, its gravitational field becomes so intense that it alters the geometry of space around it to a critical degree. It creates an invisible spherical boundary.
The point of no return.
Right. At this boundary, the escape velocity, the speed required to break free from the gravitational pull, actually exceeds the speed of light.
And since nothing can go faster than light.
Because nothing in the universe can travel faster than light in a vacuum, nothing can escape once it crosses that threshold.
So matter, radiation, light, information.
Yeah.
Anything that falls in just vanishes from the observable universe irretrievably.
A complete informational blackout. So we are left with an object that conceals its most problematic, physics-breaking feature, the singularity behind an impenetrable veil that we can never, ever peer through.
It's almost insulting.
It is practically taunting the scientific method. And this loss of information also creates huge paradoxes in quantum mechanics, which dictates that information cannot simply be destroyed.
Right, the information paradox.
Exactly. This compounding series of immense theoretical challenges is exactly what drove physicists to search desperately for alternative explanations, to ask the critical question, what if a collapsing massive star forms something else entirely? What if the math points somewhere else?
Here's where it gets really interesting, because that profound discomfort with physical impossibilities, the frustration of the math throwing its hands in the air with infinity, led physicists to theorize an entirely different kind of cosmic structure, didn't it?
It did.
A replacement for the black hole in the narrative, and that object is called a gravastar.
The gravastar. The term is actually a portmanteau of gravitational vacuum star.
Gravitational vacuum star, got it.
It falls into a category we call ultra-compact stars. Now, to be clear, if you were an astronomer observing the cosmos through a telescope, a gravastar would be practically indistinguishable from a black hole from a distance.
Because it is still wildly massive and completely dark.
Precisely. Its mass and compactness rival that of a black hole. Its gravitational pull is so monumentally intense that light still deeply struggles to escape its immediate vicinity, heavily redshifting and making the object exceedingly dark to observation.
So it looks like a black hole.
It would even bend light around it, creating the exact same kind of photon ring we see in those famous images of black holes. But the crucial, universe-altering difference lies deeply hidden in its internal structure.
Right. The gravastar basically throws out the two biggest headaches of the black hole model.
It entirely removes them. A gravastar contains no singularity at its center.
None at all.
There is no point of infinite density, no infinite space-time curvature, and therefore no location where the laws of physics break down.
And if there's no singularity?
Because there is no singularity, there is no event horizon. There is no point of absolute no return where information is lost from the broader universe forever.
So I have to ask the obvious question. If it doesn't have a singularity crushing all that matter into zero volume, what is inside a gravastar? What actually happens to all the trillions of tons of matter from the dying star?
This is where the physics transition from the merely complex to the wonderfully exotic.
Exotic is good. Let's hear it.
The theoretical blueprint for a gravastar suggests that it consists of an incredibly thin, ultra-dense outer shell. This shell is composed of ordinary matter, the supercompressed protons, neutrons, and electrons of the dying star.
Like a skin.
Exactly, a skin of dead star. But the interior of this shell, the core of the gravastar, is entirely devoid of ordinary matter.
So it's empty.
It is a vacuum, but not an empty vacuum. It is filled entirely with dark energy.
Okay, we need to pause here and really dig into this because I always hear dark energy used as like a catch-all term in sci-fi, or as the mysterious stuff that is pushing galaxies apart out in deep space.
Right, cosmological expansion.
Yeah, but mechanically, what is dark energy actually doing inside a dying star? How does it even get there?
Yeah.
From what I loosely understand, dark energy acts as a repulsive force.
Right. To clarify the mechanics, we have to contrast it with what we know. Ordinary gravity, which is generated by the mass of ordinary matter, is an attractive force. It pulls things together. Dark energy is fundamentally different. It is an intrinsic property of the vacuum of space itself. Thanks to quantum mechanics, we know that empty space is never truly empty.
Which is such a wild concept on its own.
It is. It is boiling with virtual particles popping in and out of existence, creating what we call quantum vacuum fluctuations. Under extreme conditions, these fluctuations exert a profound negative pressure.
A negative pressure.
Yes. Instead of pulling inward, dark energy pushes outward. It acts as an anti-gravitational force.
So picture this. Inside the gravastar, you have this incredibly powerful bubble of dark energy frantically pushing outward, and surrounding it, you have this ultra-dense shell of dead star matter that is desperately trying to collapse inward under the force of its own gravity.
That is the exact structural definition of a gravastar. The outward negative pressure exerted by the dark energy in the interior perfectly, flawlessly counterbalances the immense crushing weight of the collapsing outer layer of ordinary matter.
So they just lock into place.
The two forces meet, and they create a perfect, stable equilibrium. It stabilizes the immense mass, entirely preventing it from continuing its catastrophic freefall into a singularity.
It stops the collapse.
Exactly. It is an exceptionally elegant solution to the black hole problem. In a gravastar model, the mathematical equations hold up perfectly. There are no infinities, and no information is ever permanently erased from reality.
It is incredibly elegant. It fixes the math, it removes the infinity error message, and it gets rid of the monster on the map.
Yes.
But if it is so perfect, what's the catch? Like, if gravastars solve literally all of our theoretical singularity problems and make the physics work beautifully, why are black holes still the default answer in every single astronomy textbook?
It's a fair question.
Why aren't astrophysicists walking around talking about gravastars every day?
Because for 25 years, the physics community was staring at a monumental theoretical roadblock.
Ah.
It is one thing to draw up a blueprint for a stable gravastar, to run the numbers and prove that if such an object existed, it would be perfectly stable and solve our problem.
Right, the what if.
Exactly. It is an entirely different, infinitely more difficult task to mathematically explain how you actually build one in the real universe.
Ah, so they had the destination locked in, but absolutely no map of how to get there. They had the what, but not the how.
The scientific community rightfully asked, how does a gravastar form in practice? How do you start with a normal, massive, collapsing star made of ordinary plasma and dynamically transition it into this highly bizarre object with a paper-thin shell of matter and a core of repulsive dark energy?
Yeah, how did that transition happen?
For a quarter of a century, there was no dynamic solution. There was no rigorous mathematical pathway showing the step-by-step collapse of a star resulting in a gravastar.
Just a missing middle chapter.
Exactly. The model worked beautifully on paper as a static object, like a snapshot of a completed building. But the universe is a dynamic, violently shifting place. Without a mechanism showing the construction process, the gravastar remained a fascinating but unproven hypothesis.
Which brings us from a 25-year wall of frustration directly to the cutting-edge breakthrough that we are diving into today.
The breakthrough that changes everything.
Yeah, the missing puzzle piece that finally broke the dam and provided the how. And this is where the work of Daniel Jampolsky and Professor Luciano Rizzola steps into the story.
The achievements of these two theoretical physicists at Goethe University Frankfurt cannot be marginalized. What they have done is present, for the very first time in history, a dynamic solution to the field equations of Albert Einstein's general relativity that mathematically maps this exact collapse sequence.
Let's make sure we truly appreciate the gravity of that, no pun intended.
Very funny.
Because solving Einstein's field equations dynamically isn't just like plugging a few variables into a supercomputer, is it?
It's not even close.
It is trying to map the most complex, extreme, interconnected physical forces in the universe as they rapidly change over time, right?
It is notoriously punishingly difficult. Einstein's field equations are a set of highly complex, nonlinear partial differential equations.
Just the name sounds intimidating.
They describe a brutal feedback loop. Matter and energy dictate how space-time curves, and that curvature of space-time simultaneously tells matter how to move.
Everything affects everything else all at once.
Exactly. In a collapsing star, you are dealing with mind-boggling amounts of mass, staggering pressures, changing densities, and warping geometry, all interacting and shifting violently from microsecond to microsecond.
Just absolute chaos.
To find a mathematically rigorous solution that tracks that chaotic collapse from a massive sphere down to a microscopic scale without the equations breaking down or spitting out infinities, it is a monumental triumph of theoretical physics.
And the dynamic solution they found, the step-by-step narrative that the math revealed.
Yeah.
This is the part that genuinely makes my brain do backflips.
It's quite the revelation.
Because the solution shows that as the dying star is collapsing inward, the sheer extreme conditions of that collapse actually trigger the creation of a mini-universe inside the collapsing matter. A tiny, localized Big Bang just happens inside the star.
The math points exactly to that phenomenon.
It's just wild.
The solution suggests that the deep interior of this collapsing matter essentially fractures and gives birth to a profoundly new, localized space-time region.
A completely new pocket of space.
And what is most astonishing is that the dynamics of this mini-universe are remarkably similar to the inflationary period of the Big Bang from which our own observable universe emerged billions of years ago.
I just need to sit with the scale of that for a second. You have a dying star in our universe. Its nuclear fuel is gone. The weight of billions of suns is crashing inward in a terrifying freefall.
Right.
And deep inside that horrific crush of matter, a literal brand new universe sparks into existence.
Space-time essentially tearing and reforming.
And what adds to the incredible nature of this is that Daniel Jampolsky actually discovered this solution, this answer to a 25-year-old physics puzzle during his master's thesis.
Yes, as a student.
He was a student working under Professor Rizzola. It is such a powerful reminder that sometimes the most entrenched problems require a completely fresh set of eyes, an unburdened perspective to unlock doors that have been bolted shut for decades.
The narrative of the discovery is absolutely as compelling as the physics itself. Jampolsky brought a rigorous but incredibly fresh approach to the shifting variables of the equations.
He just looked at it differently.
And his crucial insight revolved around the concept of timing. If we connect this to the bigger picture, the mathematical formation of this mini-universe, this internal Big Bang, it does not happen immediately when the star's nuclear furnace shuts down.
Okay, so
No, it unfolds at a very, very late stage of the gravitational collapse.
how late in the process are we talking? Like right before the end?
We're talking about the absolute final moments. The star has collapsed to a point where it is almost compact enough to cross the threshold and form an event horizon.
Just barely on the edge.
The ordinary matter of the star is compressed to an extreme degree that literally defies normal comprehension.
So the star is basically millimeters away from becoming a black hole. And if I'm tracking the physics correctly, this extreme compression, this is exactly the regime where normal physics gets weird, right? Where quantum mechanics has to step in.
That is the core of the mechanism. When matter is compressed to that extreme, unresolved, nearly infinite degree, we enter a transitional realm. The macroscopic world of extreme gravity intersects violently with the microscopic world of quantum mechanics.
They collide.
They do, and it leaves a crucial mathematical space for entirely new physics to emerge. As Jampolsky's model explains, it is logically sound to imagine this radical event, the genesis of a new spacetime, occurring only when matter has reached this ultimate threshold of compression.
It needs that pressure to spark.
Exactly. The extreme, unimaginable density essentially acts as the catalyst, agitating the quantum vacuum and giving rise to these completely new physical effects that intervene just in time to prevent the formation of a singularity.
It's like the universe is pushed to the absolute edge of a cliff. It is on the brink of breaking its own fundamental rules by creating a singularity, but at the final possible nanosecond before it goes over the edge, it pulls a parachute cord.
I like that.
And that parachute is the creation of a mini-universe.
That is an excellent way to conceptualize it. The laws of nature find an escape hatch before they are broken, and the expansion of that new mini-universe is the final crucial puzzle piece that explains the gravastar.
Because it pushes back.
Yes,
Right.
because just like our own universe, the aggressive expansion of this newborn space-time inside the star is driven by dark energy.
So what does this all mean for the collapsing star? We've got this violent, dynamic, incredibly fast process happening. How does a tiny internal mini-universe actually manage to halt the collapse of a mass that weighs billions of times more than our sun and ultimately create the gravastar?
It results in a battle of fundamental forces on a scale that is almost impossible to truly visualize. On one hand, you have the outer shell of the dying star, the remnants of ordinary matter falling inward with unimaginable relativistic gravitational momentum.
It just wants to crush down to a point.
Right. But inside that collapsing sphere, this new mini-universe has violently ignited. And driven by the intense negative pressure of dark energy, it is aggressively and relentlessly expanding outward.
It is an unstoppable force meeting in an immovable object.
Precisely. Or rather, it is two unstoppable forces colliding. The outward, dark energy-driven expansion of the internal mini-universe violently counteracts the inward gravitational plunge of the collapsing star.
And it wins.
It creates a stalemate. Crucially, it halts that inward collapse before the matter can cross the critical threshold to form an event horizon, and before it can crush down into a singularity.
It freezes the collapse dead in its tracks.
Yes.
I'm trying to picture the mechanics of this impact. Imagine you are watching a controlled demolition of a massive billion-ton concrete skyscraper.
Okay, building on the analogy.
Right. The explosives go off, the structural supports fail, and the entire building starts plunging downward in a terrifying freefall.
Sure.
But at the exact microsecond before the falling concrete hits the ground and shatters, a massive, utterly indestructible airbag inflates instantly inside the hollow center of the building.
And catches it.
Yeah. The millions of tons of falling concrete hit the aggressively expanding airbag. But here's the thing, it doesn't just bounce off, right? The friction, the insane pressure of the concrete pushing down and the airbag pushing up, they perfectly cancel each other out.
They balance.
The building just stops falling, frozen forever mid-collapse, perfectly balanced in the air.
The demolition airbag analogy is incredibly useful for visualizing the opposing forces, though we have to add the nuance that this isn't inflating into empty space. It is inflating against the densest matter imaginable.
Right, the scale is completely different.
Vastly. The falling building represents the collapsing matter of the star. The inflating airbag is the immense dark energy pressure of the mini-universe. When those two opposing cosmological forces meet, an absolute equilibrium is established.
Absolute deadlock.
The incredibly dense collapsing outer matter is locked in an eternal deadlock with the powerfully expanding interior mini-universe. They balance each other perfectly. And that deadlock, that incredibly tense state of frozen, violent equilibrium, is the gravastar.
The gravastar is the deadlock. That completely clicks for me now. It isn't just a static, boring ball floating in space. It is a dynamic standoff between gravity and dark energy.
Exactly.
And this mathematical proof by Jampolsky and Rizala, this model showing how the mini-universe inflates to catch the collapsing matter, this is the definitive answer the physics community has been lacking, right?
Yeah. It is the missing link.
It proves mathematically how you get from point A, the dying star, to point B, the dark energy-filled gravastar.
It provides the rigorous mathematical validation for the formation process that was missing for 25 years. It takes the gravastar from being a theoretical, static what-if on a chalkboard to a dynamically viable, physically possible how in the real universe.
It makes it real.
It demonstrates that ordinary matter undergoing extreme gravitational collapse possesses a valid theoretical pathway to form this extraordinary object without ever violating the known laws of physics and entirely bypassing the impossibilities of a singularity.
So we zoomed all the way in on the microscopic mechanics, from nuclear fusion of iron to the extreme compression of electrons and protons, all the way to the birth of a dark energy-fueled mini-universe.
We've covered the very small and very fast, yes.
I want to take a breath and zoom out now.
Yeah.
Let's look at the broader philosophy of physics here. Because this discovery, this shift in how we view stellar death, says something really deep about the mindset of science itself and how we must approach the great unknowns of the cosmos.
It speaks volumes about the scientific method, and especially intellectual humility. Professor Rizala makes a very pointed and important philosophical observation regarding this breakthrough.
Oh, what did he say?
He emphasizes that actively seeking mathematical alternatives to black holes, like this gravastar model, should absolutely not be misconstrued as a fundamental skepticism toward black holes themselves.
Right, he isn't telling everyone to throw all the black hole textbooks into a fire and declare them a hoax.
Not at all. Black holes, despite the severe physical problems presented by their singularities, still represent the most mathematically natural and simplest solution to the ultimate fate of gravitational collapse, at least within the strict current framework of general relativity.
The simplest solution on paper.
They remain the path of least mathematical resistance when solving the equations without factoring in quantum mechanics.
The path of least resistance. That immediately brings to mind Occam's razor, the philosophical principle that the simplest explanation is usually the correct one.
Right, a foundational rule of thumb.
The textbook answer is usually right, because it requires the fewest assumptions. But this discovery implies that the universe doesn't always care about Occam's razor, does it?
This raises an important question about how we balance mathematical simplicity with physical reality. The tension between the simplicity of Occam's razor and the sheer chaotic complexity of the physical universe is a constant driver of scientific discovery.
It's a tug-of-war of its own.
Exactly. As Rizal points out, while black holes might be the simplest solution on paper, it is absolutely essential for scientists, especially theoretical physicists, who are dealing with the absolute extreme limits of nature to maintain an unbiased, radically open approach to what we do not yet know.
Because when you hit infinity on your calculator, you know you are missing a piece of the puzzle.
You know the map is incomplete.
You know you're operating in the dark. And when you are in the dark, you have to be willing to feel around for strange, exotic shapes. You, listening right now, think about how easy it is to just accept the standard answer.
It's human nature.
It is. You watch a space documentary, you read a science article, it says massive stars turn into black holes, and you file that away in your brain as an absolute unshakable truth. I do it too.
We all do.
But this entire discussion proves that the absolute truth of the universe is often far stranger, far more exotic, and far more complex than our simplified textbook models imply.
We must rigorously explore both the accepted wisdom and the more exotic interpretations without prejudice, because as Professor Rizal so eloquently concluded, the history of physics teaches us that it is not unusual at all for the latter to eventually become the former.
The exotic becomes the accepted everyday reality.
It has happened over and over again in the history of science. A century ago, quantum mechanics, the idea that particles can exist in multiple states at once, or that light is both a wave and a particle, was considered wildly exotic, almost philosophically absurd.
Einstein hated it, didn't he?
He had major philosophical issues with it, yes. And the concept of an expanding universe was initially rejected as an exotic mathematical error. The idea of dark energy itself was a radical, incredibly exotic proposal introduced to explain why the expansion of the cosmos was accelerating instead of slowing down.
People thought it was crazy.
Today, these concepts are the foundational pillars of modern physics. It makes you wonder how many other exotic theories, currently sitting on the fringes of theoretical physics, are merely waiting for their own Daniel Jampolsky to come along and find the dynamic solution that proves them right.
It really makes you pause and wonder what else is hiding right there in the math, just waiting to be unpacked and understood.
It demands profound humility in the face of the cosmos. We have mapped out a great deal of the universe, but the mechanisms at the absolute extremes, the supermassive structures at the centers of galaxies, the accelerating edges of the observable universe, the microscopic quantum hearts of dying stars, these are the frontiers where our current understanding will inevitably be challenged and rewritten.
We're really just scratching the surface.
The gravastar theory, now bolstered by this incredible new dynamic solution, is a perfect real-time example of that rewriting in progress.
So let's pull all of this complex physics together. We've gone on a truly mind-bending journey today.
We covered a lot of ground.
We really did. We started by looking at a massive star burning brilliantly in the dark, fighting a billion-year war of equilibrium against its own crushing gravity.
The great cosmic tug-of-war.
We watched the atomic fuel run out, the catastrophic collapse begin, and we faced the terrifying prospect of the singularity, a mathematical monster, an error code, where the laws of physics basically go to die.
The breaking point.
But then we explored an impossibly elegant alternative, a doorway out of the darkness. At the absolute final microsecond of collapse, the extreme, incomprehensible compression of matter triggers the birth of a tiny, dark energy-fueled mini-universe.
A spark in the dark.
And that mini-universe inflates outward like an indestructible cosmic airbag, violently pushing back against the billions of tons of collapsing star matter, locking it in a frozen, perfect equilibrium.
The ultimate stalemate.
A gravastar. No singularity, no lost information, just a dynamic, eternal deadlock of the most powerful cosmic forces in existence.
It is a breathtaking synthesis of general relativity, complex quantum concepts, and cosmological dynamics. It replaces a point of absolute physics-breaking destruction with a profound engine of cosmic creation.
And it leaves us with an incredibly provocative thought to chew on as we wrap up, because if you follow the logic of this discovery, if you pull on that thread, it leads somewhere deeply unsettling and deeply wonderful.
Oh, I know where you're going with this.
Think about this. If the mini-universe inside a gravastar expands, using dark energy in a way that is dynamically identical to our own universe's Big Bang, and if these gravastars form from collapsing stars within a larger parent universe,
I see exactly the philosophical leap you are preparing to make.
is it possible that our entire universe, everything we can see through our most powerful telescopes, all the billions of galaxies expanding outward, driven by the negative pressure of dark energy, is it possible that our universe is actually just the inside of a massive gravastar?
A universe inside a universe.
A gravastar that formed from a collapsing star in some unimaginably vast, older, multidimensional parent universe. Are we right now living out our lives inside the shell of a gravastar?
From a purely theoretical standpoint, fractal cosmologies, the concept of universes nested endlessly within other universes, have been debated and discussed in various forms for decades.
So it's not totally out there.
If the internal dynamics of a newly formed gravastar perfectly mirror the early expansion dynamics of our own universe, it becomes very difficult to casually dismiss that philosophical extrapolation.
It makes too much sense.
If a gravastar's shell acts as a boundary, much like our own cosmic horizon, the parallels are striking. It is a speculative leap, certainly, but one that is directly, rigorously rooted in the mathematics we've been discussing today.
It's grounded speculation.
It forces us to ask whether what we perceive as the totality of existence, the entirety of our expanding cosmos, might just be the internal volume of a single stellar remnant suspended in a much larger, older reality.
Mind blown. I want you to hold on to that thought. Let it rattle around in your head. Tonight, if the sky is clear, step outside. Look up at the vast expanse of stars.
A different perspective.
Pick out one of those bright pinpricks of light shining in the dark and just wonder, when that star's time finally comes, when it loses its billion-year tug-of-war, what kind of universe might it one day give birth to?
A deeply fitting thought to end on. The night sky is far more dynamic, far more mysterious, and infinitely more creative than our textbooks ever led us to imagine.
It really is. Thank you for taking this incredible journey with us. Keep questioning the textbook, keep looking up at the dark, and we'll see you next time.